Yeah, the question over here is correct order of relative energies of the following Shaw-Horst conformation. So we will simply convert the Shaw-Horst conformations into Newman, and that will give us a better idea. So the this carbon we are taking to be the front carbon, okay, these ones, all right, and the ones that I'm highlighting with blue, I am taking those to be as, okay, just hold on. Yeah, the ones I'm highlighting in blue are my back carbons over here. So keeping that in mind, now we are drawing the Newman. So if you see that the first one that we will see over here, this is CH3H, H, and that is going to be CH3. This is going to be H, and that is going to be H. Okay, and that is the number one molecule. Okay, where the CH3 groups are lying far apart. Okay, these are lying far apart, so this will be the stable, most stable anti-staggered. Okay, most stable anti-staggered. All right. What about the next one? Let us draw. This is like that. So we have a CH3 over here. We have a H. We have a H. Then there is a CH3 out here. So this is partially eclipsed. Okay. This is partially eclipsed and will be of a higher energy than that of the completely anti-staggered. Okay. What about the next one? That is the third one. This too is partially eclipsed. Okay. So we have a H and this H. There is a CH3. Okay. H here, H here. Now what is important to notice that these two conformations are convertible between each other if you rotate by 120 degree. So this is also, we will say, partially eclipsed and the interactions are same. So they will be of same energy. Okay. 2 and 3, they are of same energy. And the last one will be of the highest energy because it is completely eclipsed. So this is completely eclipsed. Okay, so that is going to be our 4. What is the question? Correct order of relative energies of the following Short's conformation. So if this is the energy scale 4 is of the highest energy, followed by 2 and 3 which are of similar energy, and at last we will say 1 is of the least energy. So option A is going to be the correct answer. Hello students, welcome to Sarasa classes. Now over here in the question number 9, the major product of the reaction of salicylaldehyde with one equivalent of MEMGBr followed by acid neutralization. So over here basically it is a reaction of salicylaldehyde, which is basically this, and it is being treated with only one equivalent of MEMGBr. Besides having the carbonyl group, okay, it is having a acidic proton. Okay, so what will happen? The nucleophile over here, that is Me minus, will react with the acidic proton and form methane. Okay, so it will form methane, and this intermediate will be formed. Okay, so that is going to be CH4 as the gas. This is minus, that is plus. Now this on reaction with acidified water, basically this portion will be converted to OH. Okay, that is what is going to happen. So we will get back the acetaldehyde, sorry, salicylaldehyde. So out here the molecule that will be formed is going to be 2 as the final product. Okay, and that is why over here the answer will be 2. Let's go for the next question. Over here we have been asked the correct statement about the bond angles and bond lengths in the Al2Cl6. Okay, so for the Al2Cl6, the structure is as follows: Al. Okay, so when a chlorine joint is coordinated or bonded to two atoms, that is called the bridging chlorine. Okay, so one that I am drawing right now is the bridging chlorine, and one, the chlorines attached to only one aluminium, are the terminal chlorines. So these are my terminal chlorines, and these are my bridging chlorines. Okay, now the bond angle over here, this one is 87 degrees. This one out here, it is 93 degrees. Okay, and the one out here, it is 110 degrees. Okay, bridging bonds will be longer than the terminal bonds. So these ones are 2.21 angstrom, and these ones are 2.06 angstrom. All right, so in that sense what we will say, obviously the AlCl bridging will be greater than the AlCl terminal. All right, and as we can see from the data given out here that the CLALCL terminal angle is greater than that of the CLB ALCLB. So if we compare the information that we have understood with the options given over here, then option A will be the correct option over here. Okay, next. Consider the following reaction sequence. So basically we have been given a acid chloride, which is this one, and it is undergoing Rosenmund reduction reaction. So you're using basically PD supported on barium sulfate in presence of 1 atm pressure of hydrogen. So that will lead to the synthesis of an aldehyde like this one. So this is our P. Again, if you treat this one with the Grignard reagent, methyl magnesium bromide in presence of acidic workup, it leads to the formation of Q, which is going to be something that is like that. And this one further, if it is treated with chromium oxide, so which is basically an oxidizing agent, so the 2-degree alcohol will be converted to the ketone, that is this one, which is our molecule R, and this when treated with Clemmensen reagent, that is zinc 8G in presence of Cl, HCl acid, so basically gets converted to a saturated hydrocarbon. So the product S, as it says in the statement, like this one, the product S is a saturated carbon, hydrocarbon, so this particular statement is true. The product R can undergo Cannizzaro reaction. As we see the product R over here, we will say has no aldehyde, so no Cannizzaro possible. Or rather we should say over here has alpha CH atom, so Cannizzaro not possible, but undergoes aldol condensation. Okay. Now can this R react with cyanohydrin? So this is suppose our R, and we are treating this with HCN. So the Cn minus will attack here because this is the electrophilic carbon and leads to the formation of a cyanohydrin, which is going to be that. Similarly, in the option they have asked, the products R and P can form addition products with HCN. Yes, that is true, because when you're treating with P with HCN, then also the CN can attack here and also form a similar cyanohydrine. So we will say 1 and 4 is true. Option 2 says the product Q has no chiral center. Actually, that is not true, because it does have a chiral center. This is the chiral center, having a CH3, a H, a OH, and then this is the ET. So there are 4 different groups, and that is the reason why we will say that this particular center is a chiral center. So this particular statement we will say is wrong. This one is wrong, and these are all correct. Okay. So now in the question 12, we have been asked, among the haloarenes shown below, the correct order of reactivity for the substitution reaction with NaOH. So this is basically aromatic, nucleophilic, addition, elimination reaction. And what we will say over here in these cases, that is when we use haloarenes, when we are using haloarenes, what we will say is that electron withdrawing groups attached to haloarenes increase the delta positive charge on the carbon attached to halogen. Okay. And what is the result of it? It increases the reactivity. Towards nucleophiles. In this case, we have been given what? OH minus. Alright. And how this is happening? To explain that, what I will do is I will draw the resonance structures of para-chloronitrobenzene to demonstrate how this positive charge is being increased. So due to minus M effect of nitro group, the electron density from the benzene will be pulled towards the nitro, and one can think of such a resonance structure further. This pi electron cloud can be shifted over here, and that is how the plus charge is being developed near the carbon, at this carbon which is attached to the chlorine. And so it will help this carbon to react with a nucleophile like OH minus and increase the reactivity, okay? Because this is negatively charged species which will want to come towards a carbon that is already positively charged, okay? So that is why this attack will be assisted or helped. Now what happens when you have a electron donating group? Okay, let me just create some space for us. Now whenever you have a electron donating group, something like a OMe, what is happening out here? It has lone pairs which are getting donated over here like this. That will come here like that. So now what we can see, because of the plus M effect of OMe, negative charge is being developed near the carbon which is attached to chlorine. So if there is already negative charge over here, attack by a OH group will be repelled because the carbon is already having some residual negative charge, and hence reactivity will be what? Lowered. Reactivity is lowered. What about only chlorobenzene? When we compare that with meta chloronitrobenzene. So from here only minus I is being operating, minus M is not possible. So one can say that these two will be having almost similar reactivity as far as this particular aromatic nucleophilic addition substitution reaction is concerned. So what we will say that way, that 2 is highly reactive, but 1 and 3 are almost similar, and 4 is the least reactive. Which is 4? This is 4. This is 1 and this is your 3. Okay. And what is 2? This is your 2. So that way what we will say, our answer is going to be option B. Next question is the probability density of an electron in 1s orbital for the hydrogen atom is maximum, and the options are given at the Bohr radius, at infinite distance, at twice the Bohr radius, at the nucleus. So to explain this, let us consider this particular diagram in which we have been plotting the psi square with respect to r, and as we can see, when r is almost equal to 0, we are having the maximum probability density from this plot. Okay, so that way we can say that a plot of electron probability density, that is psi square versus the r, shows that the electron density is greatest at r0 and falls off smoothly with increasing r. Okay, and if we look at this picture over here, what we can observe is that if you think that the hydrogen atom to be these concentric circles in terms like it looks like an onion, then these black dots that we see over here, we are seeing that these black dots are becoming more dense as we go towards the nucleus. So that way we can say that out here our answer is going to be at the nucleus. That is going to be our correct answer over here. Alright, in the next question, it has been asked, which of the following statements is incorrect about the complex of a divalent ion with atom number 25? Bm is the Bohr magneton. So for this, we will say that whenever the atomic number is, which is Z basically, 25, that means we will say it is basically Mn. So when we say Mn2 plus, that means electronic configuration is what? AR 3D5. So for a complex which is having octahedral geometry, and we are having strong field ligands, and let's say we are having here the weak field ligands. Okay, if we consider this, then we will say basically it will split into the T2G and the EG set. So over here we have the T2G and we have the EG. Okay, this gap, which is large, is indicating that this is a strong field. So for a weak field, the gap will be smaller. Okay, and the funda over here is what? What is the concept? That for a strong field, delta O is greater than pairing energy, and for a weak field, pairing energy is greater than that of the delta O. So out here, if we fill up the electrons, obviously the value of N over here, that is the number of unpaired electron, is 1. But when we consider the weak field ligands, over here we will see the value of N is going to be 5. Which means basically mu S, which is calculated using this formula in terms of Bohr magneton, this out here is going to be 1.73 Bohr magneton, and for the weak field case we will be having 5.9 Bohr magneton if we use the formula. For a tetrahedral geometry, okay, one has to remember that tetrahedral geometry is almost half of the octahedral geometry. So always these form high spin complex, okay, and not affected by ligand field strength. Okay, if you keep that in mind, then for a tetrahedral geometry, for say high field or a strong field ligand, this is the separation. Okay, for a weak field ligand also this is the separation, and we have to fill up the D5 electrons. So over here obviously both the cases their N will be equal to 5, and this case also N will be equal to 5. This is your T2, this is your E, this is your T2, that is your E. So always mu S value for both the cases will be 5.9 Bohr magneton. In this case also it will be 5 Bohr magneton. Now continue with the solution of IAT Chemistry 2021. Okay. Well, question of 15 is total number of stereoisomers possible for the following structures. So over here we have been given CH3, CHOH, CHOH, and this is CH3. So over here this unit can show geometrical isomerism. This one out here is a chiral center. This too is a chiral center. So for a unsymmetrical molecule, okay, the formula we will use is 2 to the power n, where the value of n, because of this unit over here, is 1. That one it is going to be 2, and that one it is going to be 3. So we will say this is having the value 3. That means it is going to be 2 to the power 3, and that is going to be total number of stereoisomers will be equal to 8. I hope that explains the total paper and its solutions for the chemistry section. Keep visiting Sarvasya classes. Thanks for listening. Have a great day.